Hello one and all. We will be continuing our course Elements of Machine Design. In previous session we have learned that how springs are classified, use of each of the spring. So there is spiral spring, there is leaf spring. Apart from that, famous one are the springs which are in form of helix. We call it as coil spring. So these springs are widely used in mechanical engineering applications. So we have learned that spring is such an element which undergo compression, you can say deflection, due to applied force. So when force is applied on a spring, it causes deflection, and that deflection is proportional to the force applied, and by that we are in position to tell that how much deflection occurs due to force, that force upon deflection. So spring index also is defined. Spring rate is force upon deflection, whereas we are in position to determine the ratio of coil diameter to the wire diameter in form of spring index C. Now we will be considering failure of this spring. So shown in a diagram is a spring which is supported, and spring has get cut. So that is called as failure of the spring. We can see in a diagram that spring has some wire diameter D and a coil diameter. It is supported from inside, and due to the force acting, there is shear occurred in the spring. So we can say that failure occurring in spring is due to shear. We have to find that how much shear stress acts on this particular spring. Indeed, there used to be two kind of shear forces acting on spring. One is the shear force which is known as direct shear force. So that direct shear force causes direct shear failure in a spring. So whatever load acting on a spring, if we consider that load is distributed over the wire, then we can say that force is shear force for that spring, and it causes likewise shearing action in a spring. What is the area which is going to resist this direct shear force? This area is shown in a diagram. So we can find that when load is acting on a spring and when it is transferred on this spring wire, spring will get cut. So the cross section is the area which is going to resist the applied force. So we can find how much direct shear stress is induced in a spring by this relation. So we write tau D, which is the direct shear stress, is equal to W upon pi by 4 D square, where D is the diameter of the wire. This is the shear stress due to whatever force is acting on a spring. So we have seen that tau D can be given by this 4W upon pi D square. Causes one more failure, and that is shown here. The failure is not occurring due to that direct shearing action, but there used to be one more shear in a spring. So by that spring will be cut, spring will be sheared off, and this is due to the deflection of spring. We know that whenever force is acting on a spring, that force causes deflection. And what is deflection? The spring length will get reduced. We say free length when no load is acting, and when load is acting on a spring, the turns tries to come closer, and these trying to come closer, we may find that there is shearing action, and that shear is known as torsional shear. Why it is torsional shear? As you can see in this diagram, that force is causing deflection and turns are coming closer. We can find that the angle of turn is changing. Angle of turn is slowly becoming perpendicular, say, to the axis of that particular spring. So spring is slightly turning. So as to come closer, wire has to be turned. As the wire is turning, we can say that there is angular movement, and this angular movement causes torsional shear stress in the wire. So we need to find the torsional shear stress induced in the spring material. So the torsional designing spring shear for failure also. The same force which is causing the direct shear is causing this torsional shear in a spring, and we will first of all find that how much is the torque which causes this direct shear. So shown in a diagram is a one turn of a spring. W is the load acting on the spring, and that load W causes deflection in a spring. So we may imagine it as a angular displacement of spring wire. So force is acting at a distance capital D by 2. Capital D is the mean coil diameter, is it? So torque can be given as force into distance. So torque is equal to W multiplied by D by 2. So we can find the torque which is responsible for this torsional shear stress. Now we will be using torsional shear formula and finding out that how much torsional shear stress will be induced in this spring. So for that sake, I have written here tau T. It is the torsional shear stress. Please remember that this torsional shear stress is also due to the same force causing direct shear. So tau T is equal to TR divided by J. R is what? It is distance of maximum stressed plane from neutral axis. We know that shear stress distribution is not uniform. So this torsional shear stress is found to be maximum at the surface, and torsional shear stress is 0 at the center, we can say. So distance of surface from center means it is small d by 2. J is the polar moment of inertia, and for round section it is pi by 32 d raised to 4. If we put it in the relation of tau T, we get W d divided by 2 multiplied by small d upon 2 upon pi by 32 d raised to 4. So what we get is tau T is equal to 8 WD upon pi d cube. So this is the torsional shear stress induced due to the force acting on the spring, where W is the load which causes deflection, capital D is the mean coil diameter, whereas small d is the wire diameter. So torsional shear stress along with direct shear stress occurs in the spring. Both are shear, are having same nature. So what we will be doing? We will be directly adding these two stresses. While designing shaft, one was the bending stress and other one was the shear stress. So we could not directly add them, right? There we have found that which is the plane where maximum stress will be acting. Maximum stress will be acting at some other plane than the plane of direct shear and that of the bending. In this particular case, we know that same force is causing direct shear and torsional shear. Nature is shear itself, so we can directly add both these stresses. So graphically it is represented here that direct shear stress is resisted by cross sectional area and it is uniform over the cross section. So distribution of the direct shear stress due to force W is uniform. So stress is uniformly distributed over the cross section. In figure B, the distribution of torsional shear stress is shown, and as we know that torsional shear stress is due to twisting action. Where twisting is more, stress is more naturally. So when you imagine that wire is rotating, its surface will be displaced more. center will not be displaced. Means at the axis, at the center, stress is 0 and at the surface stress will be maximum. So stress is increasing from center to the one of the side of the surface. So likewise is the distribution. Stress is not uniformly distributed. Both stresses we are adding here. So addition of both stresses, that is combined torsional and direct shear stress, is shown in diagram C. So what is done? Graphically both stresses are added. So this stress tau d at the inside surface plus this torsional shear stress at the inner surface, if we add, both are in same direction, so addition is there. On other hand, we can find that this is positive and this is in negative direction, so stress value will be 1 plus 1 minus, that means less. So this is the distribution of stress due to combined torsional and shear. So we can see in this particular diagram that tau is equal to tau d plus tau t. Let us add them together. So tau is equal to 4w upon pi d square plus 8wd upon pi d cube. Already we are having these relations. Now what we will be doing? We will be bringing out this 8wd upon pi d cube. So if I bring 8wd upon pi d cube outside, for this torsional shear there will be 1 plus, I have brought out 8 and there is 4 in a relation of direct shear. So what I need to do is I have to make it 8. So for that sake I will be multiplying and dividing by 2. Similarly, it is d square, so I have to divide by d, so multiplied by d, and same is the case that capital D I have brought out, so which is not present in a relation, so I will be multiplying with d and dividing with d. So it becomes 1 plus d upon 2d. So 8wd upon pi d cube into bracket 1 plus d upon 2d is the relation we will be getting. So this is the combined direct and torsional shear stress. Whatever shown in bracket is a constant, and it can also be rewritten in form of spring index as 1 plus 1 upon 2c, because we know that capital D upon small d is known as spring index, and this is constant for a particular spring. A particular spring means what? When a spring is selected, it has some diameter and it is in form of helix of some mean diameter, so coil diameter. So when coil diameter is known and when wire diameter is known, it becomes constant for a particular spring. That particular constant is known as shear stress factor, Ks. So 1 plus 1 upon 2c is known as shear stress factor and it is represented by Ks. So what will be the shear stress induced in a spring? It will be tau equal to Ks multiplied by 8wd upon pi d cube, where Ks is a shear stress factor, tau is the permeable stress for a spring, W is the load acting, capital D is the mean coil diameter and small d is the wire diameter. So we are in position to design the spring for different loading condition by using this formula. So when I have manufactured a spring, I know its coil diameter capital D, I know its small diameter small d. I may find that how much force, that is W, it can resist if permissible stress tau is known. Tau we can find from material. So if a spring material is a say high carbon steel or say alloy steel, from that particular material I will be selecting its limiting strength, that is the yield point strength, multiplied by factor of safety will be this tau. So for designing spring, this equation is important, but this equation is modified due to one more stress which is acting in a spring. We know that a spring is made shaped in form of helix, and as it is shaped in form of helix, there is curvature, and due to that curvature there is additional stress generated in the wire. There is direct shear stress, there is torsional shear stress. Apart from that, as a wire is shaped into a coil wound around a cylinder in form of helix, we can find that due to that curvature there is additional shear stress developed. So if we imagine the spring, we will come to know that inside surface of a spring has less radius of curvature. Outside surface has considerably more radius of curvature. So we can find that at inside that effect is more, slightly more as compared to the outside surface of a spring. So the fourth diagram here indicates that effect of curvature has been added. So this is the axis of spring, this is the mean diameter, so d by 2, correct. So total is diameter, so this distance will be equal to half of the diameter, it is d by 2. So this is the inside surface of a wire, and curvature effect can be found more at the inside surface as compared to outside surface. So when we consider this particular effect, there will be distribution as seen in the fourth diagram. The first diagram shows distribution of torsional shear stress. Second diagram shows distribution of direct shear stress, and combined direct and torsional shear stress is shown in the third diagram, whereas fourth diagram shows direct shear, torsional shear and effect of curvature also. So these diagrams are taken from this Khurmi-Gupta itself. We will be now designing helical spring by considering effect of curvature. We know that this is the additional shear stress. Wall has given that K, which is known as Wall's correction factor, and by using this Wall correction factor we are in position to design the spring. Here Ks is replaced by Wall's correction factor. So our new equation will be tau is equal to, let us replace Ks, tau is equal to K multiplied by 8Wd upon pi t cube, where K is the Wall's correction factor, and this Wall's correction factor considers effect of curvature. So that K is represented as 4c minus 1 upon 4c minus 4 plus 0.615 upon c. So instead of Ks, now we will be using this factor K, which is the Wall's correction factor for the helical springs. So when we are supposed to design springs without considering effect of curvature, if springs are larger, curvature effect will be very small. So spring of larger diameter, larger coil diameter can be designed by using simply Ks. In case of small springs, it is necessary to consider effect of curvature. So we have to use this Wall's correction factor especially for small springs. So it is replacing the shear stress. See here, a small and a large spring is shown here. In figure A, it is seen that spring has small d by 2, small mean coil diameter, is it? It is small diameter spring. Wire diameters are same, small d. Wire diameter is same, but coil diameter is different. First spring has less coil diameter. It shows that its curvature is more. You can feel it, that curvature is more here. As curvature is more, we are finding that the shear due to that curvature induced in a spring is more here as compared to this spring. This spring has higher mean coil diameter. This is large spring. Being large spring, its radius is more, means curvature is comparatively less here. Curvature is comparatively less. As curvature is comparatively less, we can say that effect of curvature is less in this particular spring. So we can find the effect of curvature, and as I have said earlier, in case of small spring, it is necessary to consider this effect of curvature. Now we will be moving ahead and learning about the deflection of spring. We know that whenever force is acting on a spring, there is deflection, and the turns of spring will try to come closer. We say that spring is compressed and there is axial compression. There is axial movement also whenever load is acting on a spring. And as turns are coming closer, the angle changes. Slowly turns become perpendicular. They try to become perpendicular to its axis. Thus, angular deflection in spring wire occur due to the load acting on it, and for that sake we will be using this torsional rigidity formula. So as to find how much force is acting on a spring, we have used torsional formula, where we have designed spring on the basis of strength. We have considered their stress. When we are considering deflection, we will be using rigidity part of that. So T by J is equal to G theta upon L. While designing shaft also, we have designed shaft on the basis of strength and on the basis of rigidity. So here we are considering strain as a limiting factor. So especially in ductile material, we are supposed to consider this rigidity. Here, so as to find deflection of helical spring, we are going to design spring based on torsional rigidity formula, where theta is the angular deflection and L is the length of spring. You can say length of that wire. T is the torque and J is the polar moment of inertia for that spring wire. So theta becomes TL upon JG, where T is equal to W d by 2. We know that this is the twisting, and twisting is due to load, and when load is considered is acting on a wire, so distance will be capital D by 2, considering that force is acting at that circle having diameter D. So torque is equal to W D upon 2. How to find length of spring? To find length of spring, what we are supposed to do? We will be removing its helical shape and measuring its total length. Okay, so that will be total length of a spring. So in practice it is not possible. So in practice, how we can find length of spring? It is length of one turn multiplied by number of turns provided on the spring. So length of spring can be found by length of one turn. One turn means it is in form of helix. So one complete revolution. So it is pi d. Is it? Length of one turn will be pi d, and number of turns are represented by n. So length of spring can be given by this relation pi d into n. For circular section, we know that J is equal to pi by 32 d raised to 4. So we will be putting this into equation. Theta is equal to TL by Jg. What we get? Theta is equal to T. T is W capital D by 2. Length of the spring is pi d multiplied by n upon j, pi by 32 d raised to 4, and a g which is modulus of rigidity. So this is theta. Theta is angular displacement of this spring wire. So we will be getting this relation. Theta is equal to 16 W d square n upon 4 GD. So deflection of helical spring we have found theta. So the triangle shows relation in between linear displacement and angular displacement. So we may imagine this as one turn. This is the turn. So when force is acting, this angle slowly reduces and trying to become horizontal. So this is angle theta. So when no load is acting, theta is the angle, and this is the distance in between two turn. One turn is here and say another turn is here, so it is delta. So we can say that when force is acting on a spring, angular deflection theta occurs, and as turn is moving, its moment due to force is delta simply. Is it? Theta is the angular displacement and delta is the axial displacement. So when angular displacement occurs, the linear displacement also, or say axial displacement also occurs, and the horizontal distance is d by 2. So let us correlate that. Delta can be given as theta d by 2. So we will be taking tan theta is equal to delta upon d by 2, and we will be finding delta is equal to theta multiplied by d by 2. So we get delta as 16 W d square n upon g d raised to 4. Now multiplying it by d by 2. Theta we are putting what we have calculated earlier multiplied by now capital D by 2. So we will be getting the axial deflection occurring in a spring by this relation 8W d cube n upon g d raised to 4. So axial displacement, or say deflection of a spring, can be given by 8W d cube n upon g d raised to 4. Let us replace capital D by small d by c. So we get one more relation. Delta is equal to 8W c cube n upon g d. To find deflection, we will be using the relation. Now we will be solving problem based on both. So a helical spring is made from a wire 6 mm diameter. So diameter of wire, that is small d, is equal to 6 and has outside diameter 75 millimeter. So outside diameter DO is given. We are supposed to find mean diameter. If permissible shear stress is 350 MPa, so tau becomes 350 MPa, so 350 Newton per mm square, and modulus of rigidity is 84 kilonewton per mm square. So 84 into 10 raised to 3 Newton per mm square. We are supposed to find the axial load which the spring can carry and deflection per active turn. So this is the data given. Now let us find mean coil diameter. We know that outer diameter minus d, right? Mean coil diameter d is what? DO, outer diameter, minus half the radius on one side, half the radius on another side. That means d by 2, DO minus d by 2 minus d by 2. So that becomes DO minus d. So mean coil diameter becomes 75 minus 6, that is 69 millimeter. Spring index is ratio of mean coil diameter to wire diameter. So 69 upon 6, it becomes 11.5. Initially, we will be neglecting effect of curvature. So we will be considering here that it is large spring say, and curvature effect is very less, so can be neglected. In this case, we will be considering the shear stress factor Ks, and that is given by 1 plus 1 upon 2c. So find Ks as 1 plus 1 upon 2 times 11.5. C is 11.5. So Ks comes out to be 1.043. Now we will be finding shear stress induced in a wire by the relation shear stress is equal to Ks multiplied by 8Wd upon pi d cube. So we will be putting shear stress as 350, Ks is 1.043 multiplied by 8, W is unknown, we are supposed to find axial load, multiplied by mean coil diameter 69 upon pi wire diameter cube, 6 cube. So we will be getting W as 412.7 Newton. When we neglect effect of curvature, spring is able to take 412.7 Newton force. We are considering effect of curvature. Before that, let us find deflection per active turn also. So we know delta, which is the deflection, axial deflection say, is given by 8W d cube n upon GD raised to 4. It is asked to find deflection per active turn, means deflection per number of turns. So delta upon n equal to 8W d cube upon GD raised to 4. So what will be the deflection of each turn? Delta upon n, 8 multiplied by W, it is 412.7 multiplied by 69 cube upon 84 multiplied by 10 raised to 3, it is value of G, into 6 raised to 4. So delta by n comes out to be 9.96 millimeter. So every turn will deflect by 9.96 millimeter. Now we will be considering effect of curvature, and so as to consider effect of curvature, we will be introducing Wahl's stress concentration factor K, and that is given by 4c minus 1 upon 4c minus 4 plus 0.615 upon c. C we have calculated, so we will be putting C 11.5, we get K as 1.123. We will be putting this K into the relation of tau. Tau is equal to K 8WD upon pi d cube and finding W here. So we will be putting the values, only W is unknown. So if we calculate, we will be getting W as 383.4 Newton. See, when we have considered effect of curvature, its load carrying capacity has reduced. Earlier it was taking 412 Newton load. Now spring is able to take less load. It shows that we have to consider effect of curvature because it is going to weaken the spring. So W in this case comes out to be 383.4 Newton. Now we will be finding deflection per active turn. So delta upon n, so that is given by 8W d cube upon GD raised to 4. W considering effect of curvature, we will be putting here. So same 8 multiplied by W is now 383.4 multiplied by 69 raised to 3 upon 84 into 10 raised to 3 multiplied by 6 raised to 4. So delta upon N, deflection per turn becomes 9.26 millimeter. Thus, we are in the load and deflection occurring in a spring. Now we will be having one more problem. We are supposed to design a spring. For a spring balance, we know that spring is used so as to measure the force, and spring balance is going to measure the weight. So range is 0 to 1000 Newton over scale length 80 millimeter. It shows that scale length is 80 millimeter. So as W increases, the deflection of spring increases, correct? Spring deflects more due to the load. So here is a tension spring, is it? So 1000 Newton load causes 80 millimeter deflection, say. So what is the range? 0 to 1000 Newton. For 0, we will find that the tension spring will show 0 deflection, and as the tensile force increases, tensile force on that spring of spring balance increases, slowly deflection will increase, and for 1000 Newton there will be deflection of 80 millimeter. That we are supposed to understand from this problem. The spring is to be enclosed in casing of 25 mm diameter, means as spring is to be placed in an enclosure of 25 mm diameter, maximum diameter, that means outer diameter of spring should be up to 25 mm, not equal to or more than 25 millimeter. So we will be trying to keep outer diameter below 25. The approximate number of turn is 30, N given 30. Modulus of rigidity is 85 kilonewton per mm square. G is given. We are supposed to calculate maximum shear stress. So delta relation I have written, that is equal to 8W C cube N upon GD. I have used relation of C. So putting values, unknown is C, which is not given, and the wire diameter also not given. So C cube upon D becomes 28.3. Be choosing wire diameter of 4 millimeter. Here both diameters are unknown. So what we will be doing, so as to decide, so as to determine the coil diameter, we will be taking wire of diameter 4 mm. So if we put D is equal to 4 in above relation, C cube upon D is equal to 28 upon 3, what we get? C is equal to 4.48, and what will be the capital D? C multiplied by small d. So capital D, mean coil diameter, becomes 19.36 millimeter. D is the mean coil diameter. We are supposed to find outer diameter, so that spring can be placed in a casing 25 mm diameter. So let us find outer diameter DO. We know mean coil diameter plus radius on one side and radius on other side. So D plus D by 2 plus D by 2. So D plus small d comes out to be 23.36 millimeter. So 23.36, yes, the spring can be fitted in a casing with diameter 25 millimeter. So thus we are supposed to use this spring. K we can find now for this spring, which is 1.322. Maximum shear stress is to be found. So it is given by tau is equal to K W D 8 upon pi d cube. So putting all the values, K we have calculated, W is known, 1000 Newton is the maximum reading which we are supposed to take, multiplied by D we have selected, wire diameter is 4. So maximum shear stress induced in this particular spring will be 1018.2 Newton per mm square.